Mm, okay. So the last thing was we talked about that you have to understand three things so far from the ODE. The order of the ODE, is it autonomous or not, and the order, is it autonomous or not, and is it linear or not. That's the terminology so far for, no, there's one last terminology, then we're gonna end up the terminology for the ODE and start doing actual math. But before that, we said in the first lecture, or in the first video series, that the ODE can have a solution, no solution, or infinitely many solutions, and we have to focus on these things right now. So let's take an ODE. And first, let's say the properties of this ODE, since we actually covered it in the last video. First thing, this is a non-linear because we have a square root, because we have the square root of y, or square root, that means what is the square root of y, so we have a square root, so this is a non-linear thing. This is not autonomous because we have x, which is appear, time y, but that's because x does appear. And lastly, it's of a second it's of a first order of it's a first order because we just have the first derivative. So, and the most problem thing here is that non-linear can make a lot of things, goes like crazy. So if you want to solve, let's guess the solution of this thing, and let's talk first. I haven't actually said what the solution is. Once we're talking about ODE, we're talking, as I said, I think we're talking about the solution. We are searching for a solution which is a function or something that actually satisfies this thing. Most of the time it's going to be a solution, a function. So, for example, if we have a second derivative with respect to x is equal to 0, then we're actually looking for a function. Anything that satisfies this thing is a solution. For example, x is equal to 0, put it back, differentiate x, differentiate 0, y is equal to 0 because we are talking about, we want to find the y. We want to find the y. So y equal to 0 is a solution because we differentiate y. First time you get a 0, differentiate it again, you get 0. So 0 is equal to 0 is a solution. Y is equal to 3 is also a solution because differentiate it first time you get 0, differentiate it again, you get a 0. Y equal to 3x is a solution. Y equal to 3x plus 3 is a solution. So that's the solution. And once we're talking about solution, we're talking about the solution in an interval. So we're talking about solution in an interval. We are talking about math. So maybe this thing, so like this solution, this thing does satisfy this thing in this interval. It means it not satisfied in the open, more general interval. Maybe it's only satisfied in some specific interval. So we have to understand this thing. So for example, if we put this thing as x, we're looking for a function whose second derivative is equal to x, and then I said only it's not like an interval, only in the interval that x lies between 0 and 0. So for this thing, we can put y is equal to 0, because if we differentiate, because x is just 0, from this implies that x is equal to 0 in this interval, and if we differentiate 0, you will get x which is 0. But if we're talking about if we're talking about an interval of real number, this won't be true. So we have to be careful about the interval in which we are talking about. So the solution, as we saying the differential equation, we actually most of the time we just, this is the course, this is how the course can work. We say a solution, we get a solution, or we get a method in which we can find the solution, then we do some adjustment to the guessing and we find out the general solution. This is how the course is going to work like, and I'm trying to make it as informal as possible. So I may not discover, of course I won't discover, but I may not discuss the how, I may not discuss why is the case. Maybe I'll just separate playlist. So this is, so once we start here, so we are actually looking for a solution for this ODE. First thing that may come into the mind is y is equal to 0, because if you put y equal to 0, this will be 0, and differentiate 0, it will be 0. So this is a solution. Y equal to 0 is a solution, and y is equal to, let me see, x the fourth over 16. It's another solution. It's another solution. So there is more than one solution. Well, now someone may say that's okay, because we have the first derivative, but that's not always the case. Yeah, and if you want to study differentiation equal to 6, you can say that y is equal to 6x plus c, where every solution is different by c. But sometimes in differential equation there is only one solution, and as we see in other cases there's actually maybe no solution at all. Or you may also say that okay, there is more than one solution because we did not specify the initial conditions, or because like in this case, if we put x equal to 0 and 0, so if you know that okay, we say this curve gonna pass to one point, so in this case we may say that okay, we did not specify which point in which the curve gonna pass, because for example if we say this is gonna be the same, this case is gonna be the same case as this one, just specify a point and you're gonna find the c, value for c. But you're actually gonna see that this thing is not the same, this differential equation is not the same as this differential equation. This differential equation, the solution is not unique even if you specify the point. For example, if we say that this differential equation, okay, we want it to pass to the point 0 and 0. Both of those functions does pass between the point 0 and 0. There's 0 for all the value of x, so that's pass through 0 and 0. With this thing x equals to 0, you get y equals to 0, so it does pass the point 0 and 0. So there is no unique solution even if you specified a point in which the curve is going to pass through. Another higher, I just love this example because I love visualizing this example. If we take a function such as the second derivative of y minus y is equal to 0, So this is second order. Okay, so this is a second order. This is second order linear. There's a second order linear ODE. But imagine if you say, okay, we're gonna choose 2 points. The curve gonna the function gonna satisfy, and we're gonna choose 0 and 0 and 2 and pi and 0. So if the way I think about it, so imagine if you have like this is the function, this is a function. So you have a function that goes maybe everything, and you say, okay, I'm gonna nail it here, I'm gonna nail it here. The thing about this one, that there's actually an infinite many solution. Just think about it. So there's this function that satisfies that thing. You can also change the amplitude, as we're gonna see that actually if you change the amplitude, so maybe one, okay, instead of this, so make it big. Then, no, I'm not going to get it drawing. So change the amplitude to make it big, then down, then big, then it goes down. This is also a solution. Why? Because the scaling that was for this equation, the vertical scaling would affect the slope. Won't affect the second derivative. I mean, it's not the slope. I mean, it won't affect the curvature for this equation. For example, if this was a sine of x, this is an example. This is a solution to say, okay, put a equal to 1. So this is the amplitude equal to 1. If you put the function is a sine 2 is 2 sine of x, and you put it back, and also it's also it's not also a solution, because let me see, or let us see that if you differentiate the first time, it's gonna give you cosine. Differentiate again, it will give you sine of x with a negative. The original function was 2 sine of x. They tell you no. So this should think it should be positive. Sorry for that. So second derivative of y plus y equals 0. If you add this one and add that one, add the second derivative and add the first derivative, it should give you 0. So this is a solution because it does satisfy the ODE, and that's the definition of solutions. A function or something. If you don't consider y equal to 2 as a function, it is a function. So the solution of ODE is a function that satisfy the ordinary differential equation. So in this case, okay, you can have a string that's gonna pass through that thing, like a wave that's gonna pass through that thing with this equation, and then you can also switch the wave and the curvature of the second derivative, the relationship to the second derivative of the function, that won't change. Which is kind of interesting, because if you stretch the function vertically, this relationship is still hold, and we gave it 2 initial conditions, and still we have infinite many solution. Imagine also you can give this thing actually not only 2 solution, 2 condition. You can give it infinite many conditions. Like 2 pi and 0, 3 pi and 0, and so on. And we're still gonna have infinite solution. So right now we found something that have infinite solutions, and can a differential equation have no solutions? Let me see, or let us see. Imagine we have a first derivative square is equal to -3, and we're working in the real number. So real numbers. So by the way of working with the real numbers, you say, okay, you just told us this is actually a function, this is a function. Okay, I mean that the function that exists, the domain of the function is in the real numbers. So the domain is in the real numbers. Oh, it's true for all the real numbers. So no matter what you put x out for the independent variable, this thing also gonna hold. So, but for that, let us see the properties of this ODE as a last example of the type of the ODE. This is a first order, non-linear, autonomous ordinary differential equation. We're working with them, so right now this is a problem, we find their function, once we square it, we get -3, and we're working with the real numbers. So the output of the function then be in a real number. And differentiation, it makes you stay in the same domain that you work with. So I know that I said a lot of information, but let's see what I mean. I mean, if you are working with a function of real numbers and you differentiate it, you're gonna stay in the real numbers. So this thing, if you call it as a function, y prime is a function, we know it's a function, so the y prime is in the real numbers. But this real number, once we square it, give us a negative number. We know that there's no such real number that we are talking about. So this function, this is ODE, or this last ODE, this ODE has no solutions. So we want a way to know when an ODE has a solution, when an ODE does not have a solution, or when an ODE have a unique solution, because some immediately you got an ODE, you just guess this or the solution, you guess. I think this is the solution. I think that this is the solution, and you end up saying, no, there's many more solutions. So we must know if the ODE is the solution is unique, or if it does exist, because you don't want to waste your time in a solution that does not exist. Or if it does exist, or it does not, or there's infinite unique does exist, or there is not, there is unique does not exist, or does is not unique. So those two stuff we're gonna cover in the next chapter.